Hello, I'm Sean. I hope everyone is staying safe and healthy during this MCO period. And today, finally, we have our YouTube channel. This channel is all about maths, specifically maths for now. And today we have our first lesson. Before we move on to our first lesson, let us go to our class. Let's go.
Alright, welcome to the class. Today we will talk about how to convert decimals into fractions. So this is a newly added topic in the new Form 4 KSSM syllabus. So I think it would be great if I can make a video on this new topic. Let's start off with an easy one. Let's say we want to change 0.5 into fraction. So what we can do is that we can put this 0.5 to be the numerator and then make it over 1. After that, we just need to keep on multiplying 10 to the numerator until the numerator becomes an integer. So for 0.5, we just need to multiply 10 for once to make it an integer. And another one time at the denominator to make it balance. So now what we have is that we have 5 over 10. And when we simplify this, we will get 1 over 2. This is usually what we do if you want to change rational numbers into fractions. But unfortunately, this is not what you will see in your syllabus. So what you will see in your syllabus is something like this. You will have 0.5, 5, 5, 5 again, and 5 again, over and over again. Okay, so now if you use the same trick to change it into fraction, a problem we will face is this. Let's take this to be the numerator. And then we divide by 1. So now the question is, how many 10 do we need to multiply at the numerator so that it will become an integer? Anyone knows what's the answer? The thing is, we couldn't know because this is having infinite amounts of decimals. That's why we couldn't tell how many 10 we need to multiply to the numerator so that it will become an integer. So that's why this method doesn't work in this situation. Okay, so we've mentioned that the problem comes from the indefinite amounts of decimals. Okay, we don't know when it stops, right? So if we can remove the indefinite decimals, then we can actually change it into a fraction. So now what we need to do is to actually let this number to be an unknown, any unknown that you like. Let's say x. So I'm just going to write 3 times of 5 because it's too long. Alright, so we let this long number to be x. And now what we need to do is to make another equation such that we have another number that has the same recurring decimals as this x. So what we can do is that we can multiply this x by 10 and we will have 5.555 on and on and on. Alright, because we have many 5 at the back, so when we multiply by 10, this goes to here, we still have many 5 at the back. So now we're going to do some calculation with these two equations. So I'm going to define this as the first equation and this as the second equation. Okay, so here comes the trick. So if I use second equation to minus with the first equation, I will have 10x minus x and 5.555 minus 0.555. So I will change this into vertical form and it will look something like this. I have 5.555 minus 0.555. So what we can see is that all these 5 will be cancelled by each other and we have 0, 0, 0 at the back. Since all of these are 0, we can actually ignore it, okay, and what we have in remaining is 5. Okay, so here you will have 5 and here you will have 9x. So now express it in terms of x, we will have x equals to 5 over 9. At the very beginning we have defined x as the decimals and now we have also found that x is 5 over 9. So which means we can say that this decimals, this recurring decimals is actually 5 over 9. Okay, so now let's try to use the same approach on another question. Let's say this time we have 0.212121 over and over again, and we let this number to be y this time. Why do we want to let it to be an unknown is because later on we are going to derive another equation from this equation. So denoting this number to an unknown will make the task easier. Okay, so now our objective is to make another number such that this number is having the same recurring decimals as this. We can see that the pattern is having 2 1 2 1 2 1 over and over again, right? So I'm going to make another number that is having this 2 1 2 1 2 1 pattern. So in this case, I will multiply the first equation with 100. So after I multiply it with 100, I will have 100y equals to 21.212121 over and over again. Why 100? Because if you multiply by 100, right, I will have the same pattern at the decimals. And now I will denote this as the second equation. So what we're going to do next is the same thing. We're going to use the second equation to minus with the first equation. So what it does is that we will have all these recurring decimals to cancel off with each other. Okay, we will have 100y minus y, so we get 99y. And this number minus with this number, all the recurring decimals will be cancelled off. And in the end, we will have 21. So simplifying this, we will have y equals to 21 over 99. And further simplifying this, we will have 7 over 33. Alright, so here's another little trick that I would like to show you. You can actually key in these long decimals into your calculator and let it convert for you. Make sure the decimals that you're keying in is long enough, and then press enter. You will have the fraction. So let's try out with this example. Again, we key in 212121 over and over again, and make sure it is long enough, and then we press enter. We have 7 over 33. This trick will work like a charm for the simpler cases, but for the case where you have more complex pattern, we still have to go back to the equation method. Let's say we have 3.14485. Okay, let's try out with the calculator. We key in 3.144854854 over and over again, and make sure it's long enough. Press enter. Now it still remains as decimal. So in this case, we still need to go back to the equation method. The approach is still the same. Now we need to let this to be an unknown. Again, I will let this to be x, any unknown that you like. Since the pattern can be seen as 485, so I'm just going to write halfway. I'm not going to write too long. Okay, so in this example, we can see that the pattern only occurs at the back here, at least not at the front, the 1-4. We need to determine where does the pattern start. So in this case, when I scan through here, I see that the pattern actually starts from here, 485, and then 485, and then we have another 485 over and over again. Okay, so this is a pattern. So now I'm going to make two equations such that these two equations is having 485 after the decimal point. So in this case, the first number that I can think of is this. I can multiply by 100. Okay, I will have 100x equals to 314.485485 over and over again. And the second number that I can have is this. I can multiply this by another 1000. Okay, so I will have 100 and then 3 more 0 equals to 314.485485 at the back. So now we can see that this equation, first equation and the second equation, is having the same recurring decimals. So it means that we can actually use the second equation to minus with the first equation to cancel off all the decimals at the back. So if you use this, 100,000x to minus with 100x, we will have 99900x. And on the right, we will have 314,485.485485 minus 314.485.485. Cancel off all this, we have 0, 0, 0, and here we will have 314,171. So to solve the x, we just need to divide by this number. In the end, we have this as our final answer. Let's check our answer using a calculator. A fraction 314,171 over 99900. Enter. You have exactly the same answer. Alright, so in the end, you can always use your calculator to check the answer for you.
Alright, that's all for today's video. If you find it helpful, don't forget to hit the like and subscribe button. And also, if you'd like to learn more from me, you can message me on my Instagram to join my weekly class. Any questions? Feel free to ask me in the comment section down below. And I will see you in the next video. Bye.